Hi students, I welcome you to the course on Advanced Computational Techniques, the role of nonlinear optics in optical computing, need for new materials. Nonlinear optics in optical computing, how we do operations with nonlinear optics. We will discuss elaboratedly in this lecture. The role of nonlinear optics in optical computing, need for new materials. This section explains the importance of nonlinear optical materials. This section, this section explains about the importance of nonlinear optical materials. These materials are essential for optical computing. Many scientific disciplines contribute to this field. Many scientific fields are actually contributing to this field. Let's see importance of nonlinear optical materials. See, nonlinear materials interact strongly with the light. They interact very strongly with the light. And thus, they can change light properties such as color or energy. They enable optical devices to function it. They enable optical devices to function. See, NLO materials can change the color of light from being unseen in the infrared region of the color spectrum to the green color where it is easily seen in the visible region in the spectrum. This kind of high energy transmission cannot be actually possible in any other things. So nonlinear optics is actually allowing that. No. Limitations are the for current materials. Many optical devices require efficient nonlinear materials. Existing materials need high energy to switch from one state to another state. More research is needed to improve material performances. NLO materials based research is actually required to improve the performance. So organic nonlinear materials, they are organic materials have strong nonlinear behavior. Organic materials are actually having strong nonlinear behavior. They are also flexible in design and they are resist optical damages. By means of optical, nothing is going to happen to them. But processing them into crystals and films is difficult task. See, the organic materials need to be actually formed as a crystal, or they need to be actually formed as a fiber, which are actually crucial point. Phthalocyanins and polydiacetylens are promising candidates for these purposes. Phthalocyanins and polydiacetylens are promising materials. Phthalocyanins are ring-shaped porphyrin molecules. They have large and ultra-fast nonlinear response. They have large and ultra-fast nonlinear response. See, they are, phthalocyanins, they have large and ultra-fast nonlinear response. They show strong visible electronic transitions. In the visible region, they show strong visible electronic transitions. They withstand up to 400 degrees Celsius. These phthalocyanins withstand up to 400 degrees Celsius due to the ring shape of the porphyrin molecules. They are used in photovoltaics and photoconductive applications and also photoelectrochemical applications. On the other side, we have a polydiacetylens. They are zigzag polymers with mobile electrons. The electrons can actually the mobile one. They have high electronic nonlinearity. Polydiacetylens having a high electronic nonlinearity. Their response time is sub-picosecond. They are suitable for high-speed optical switching. They are suitable for high-speed optical switching. Some show intrinsic optical bistability, but bistable devices act like optical transistors. See, let's see about optical logic gates. Logic gates are essential for digital computing. Optical logic gates switch light with light. Optical logic gates switch light with light. NASA had demonstrated optical switches using phthalocyanines and polydiacetylens. Phthalocyanine device works as AND gate at nanosecond speeds, and polydiacetylene devices behave like NAND gate in picoseconds. Okay. See, AND gate demonstration here. See, two collinear beams pass through a phthalocyanine film. Let's go there directly here. There are going to be a phthalocyanine film. Okay, here it is. There are two laser lights, two collinear beams. Okay, one and 532 another one. Okay, this one. Okay, this one. Okay, and another one is this one. Okay, two collinear beams pass through a phthalocyanine film. Simple. Filter blocks one wavelength and allows another. Filter blocks one wavelength and allows another to pass. Output beam pulses in sync with the input laser. See, the output pulses is actually very synchronization with the input laser. This behavior matches with the AND truth table. And these all conditions are actually been happening only at one state. When both the inputs are there, then it is actually doing the output, as we have discussed. For example, any one of the wave is not actually being illuminated, and this behavior will not be actually experienced, so that we get output as 0. Okay. The same thing in terms of fiber we have actually taken in the earlier case, but here we take, sorry, film we have taken in the previous case, but here in terms of fiber. Okay. It's a similar configuration, but using polydiacetylene coated hollow fiber. This one, okay, this region. Sorry. So, yes, okay. Polydiacetylene coated fiber optic. Okay, fiber. Sorry, it's a fiber, hollow fiber. Laser pulses induce fluorescent signal. Laser pulses when it is actually falling on a PDF fiber, it creates a fluorescent signal. Signal disappears when second beam is turned on. Signal get disappears when the second beam is turned on. This actually matches with the NAND characteristics.